So hello and welcome friends to our channel Intromech, and we are discussing about the metal forming processes. In the previous lecture we have seen the rolling process, and now we will look for the wire drawing process. Now what is a wire drawing process? It is a process in which this is a die which is fixed, okay, and the rod is pulled through this die having a cavity, so this rod gets converted into the wire. So this is nothing but a wire drawing. Now let's say this bar is having diameter du as original, and finally we are getting a wire having a diameter d1. Now we are pulling this rod through this die, so there will be stress. Let's consider it as a sigma 1, okay, and we are pulling this, so let's consider this as a sigma 2 because we have to apply some back tension also, which is a sigma 1. So sigma 2, we are pulling this wire. Now this has a different zones. So the first zone, this is called as the deformation zone, because at this zone this rod of diameter d is getting converted into the wire of required size. So this this first section is called as deformation zone, okay. So this is our deformation zone. Now what happens in this deformation zone? This die has a say die angle which is 2 alpha. This is also called as deformation angle. Now this is our die angle. Now this die angle is different for different materials, and it varies from 20 degrees to 48 degrees. Now the smaller die angle is used for hard materials, and the larger one is used for soft materials. Now as it has a conical shape here, right? Now when we pull this material through this die, there will be friction on this wall. So let's zoom on say this area. Let's consider this area. So here if we see, this is a slant portion, right, and we are pulling this rod in forward direction. The friction force will be acting in backward direction. Let's consider this friction force as F, and if we resolve this into two components, and this will be our alpha, so this will become F cos alpha, and this vertical force will become F sin alpha, okay. So in this region this friction force is acting, and this is our horizontal component and this is our vertical component. Now because of this horizontal component, it is in opposite direction of the pulling, so we have to apply more force if this force is larger than 1, because it is applying it is resisting the pull force of this material, and this vertical force is acting on the walls of this die, so it may damage the wall of the die. So this is important to control this angle, or say this is why these materials have these specific angles, because these angles affect the friction force which is acting, okay. So this is the importance. And say now we have a zone 2. So the zone 2, this zone 2 is called as entry zone, or it is called as lubricating zone. This is lubricating zone because as we have seen in first zone there is a friction, so in order to reduce the friction we can apply lubrication from this entry region. So this is called as lubrication zone. The lubrication can be a liquid lubrication, or in some cases the solid lubricant like graphite, mica is also used, and the quantity of lubrication is also required to be controlled, because too much lubrication can also affect the quality of the job. So this is the lubricating zone. Now the third zone is called as sizing zone. This is an important zone, because in this zone the rod of diameter D gets converted into the rod of diameter D1, but the requirement is this cross section should be uniform. So that is very important. The cross section should not vary. So when this material goes into the plastic zone, there is some elastic recovery in the plastic zone also. So in order to allow the material to properly enter into the plastic zones, and there should not be any elastic recovery, this length is kept specific, which is around 2 meter to 5 meter. So this is the sizing zone length, which is kept around 2 meter to 5 meter. So that is, this zone is very important. And in this zone actually we are sizing the rod, that's why it is also called as sizing zone. Now moving on to the next zone, which is our fourth zone, and this is exit zone. We can see here like the wire is getting drawn and getting exit from this die, and here we have a cover in order to avoid the splashing of the lubricant. So this is our exit zone. Now let's check some basic terminologies here. Now we have our DO, say a rod diameter, okay, and we have our D1 which is our required wire diameter. So AO is area which is corresponding to DO, and A1 is the wire area, cross sectional area, right? This is rod cross sectional area. Okay, now there is a term called as draft, which is denoted by K, and it is given as AO by A1, which can also be written as D1 DO by D1 square. We just substituted the values of area here, and we get this draft. So this is an important term, that how much ratio, it indicates the ratio of the initial wire diameter square to final wire diameter square, or initial area to final area. So this is called as draft. Then there is another term which is called as percentage reduction in area, because the area is getting reduced. So the percentage reduction in area, let's consider it as a J, and that can be given, it is reduction. So AO it will be larger, A1 will be smaller, and again A0. So that will be my percentage reduction. Say into we can have 100, so that will give us percentage reduction. If you multiply it by 100, we will get percentage, otherwise we will get a value in fraction. So that is our reduction in area. Okay, so this is our reduction in area. Okay, so this is the percentage reduction. Now moving on, we have, as we have seen here, we have friction here. So there must be a coefficient of friction. So let's say mu, and we all know that that can be find out as tan into beta, where beta is our friction angle. Now, then we have 2 alpha. We have seen it is at a die angle. Then L is our length of deformation zone. That is important. That is length of deformation zone, because the material is getting deformed in this zone. So that is our we have seen the deformation zone. That was our first zone, and the length of that zone, that will be the deformation zone. Then again we have a constant value which is denoted as B and is calculated as mu into cot alpha. So this is a term which is required for stress calculation also, and then again the force which is required to pull this wire. Then with all these constants, the sigma 2 stress, this value can be given, as we are not going into the derivation, so this value is given as like this. B is constant, so this is 1 minus, we have AO, sorry, here it is A1 by AO raised to B, plus we have A1 by AO raised to B into sigma 1. Now this sigma 1 is the back tension which is applied, and we have seen this value. So this is back tension value. Now this is how the sigma 2 is calculated. Now the question is, this sigma 2 should be greater than or equal to or less than the yield strength of the material. Now many of you might think that as we are going into the plastic deformation zone, this value should be greater than the yield stress of the material, but this is not the case. This sigma 2 value should always be less than or equal to sigma y of the material. And why? So when we are pulling the material, we are applying a stress of sigma 2 at the outer end, at the exit zone of the wire. So if this stress is greater than the yield strength of the material, then what will happen is, when the wire gets pulled out of the die, at that time also it can be deformed permanently, and we cannot get a constant cross-sectional area. So that is why this sigma 2 should be less than sigma y, and in the maximum case that sigma 2 can be equal to sigma y. Now we are pulling this wire, so definitely there is a drawing load. We are drawing the wire, so how much that drawing load is. So if we consider drawing load, let's say DL, so this can be again a simple logic. Stress we all know as force upon area, so this load is nothing but a force that can be given by sigma 2. This is the stress, and A1, this is the final wire area on which this stress is getting induced. So this is the cross-sectional area of the final wire, and that's why we are considering here A1. So this is our drawing load. Now again, in this case we have not considered the frictional force which we have seen. Okay, frictional force not considered, right? So this is only the drawing load, but if I want to overcome this frictional force also, which is required, so that's why we have to go for the total drawing load, which also takes into account the frictional force. Okay, so this total drawing load, now when there is a frictional force, this sigma 2 value, let's consider it as a sigma t, that is a total stress, and that becomes sigma y, plus we have sigma 2 which is we have seen is lesser than the sigma y value, then this into sigma y, and e raised to minus 2 times we have mu l divided by r1. Now here mu is the coefficient of friction, L we have seen this is the length of the deformation zone, then r1 is radius, so that will be our final d1 wire diameter divided by 2. So from this formula we can have a sigma t, and then we can have a total drawing load as sigma t into a1. So here we have to consider this sigma t, so that is my total drawing load, because I am considering the friction also. That is why it is sigma t, and this is we have considered as total drawing load. Now power we all know, like here it is a load, so force into velocity is nothing but the power. So with how much velocity we are drawing that wire is required, and from that we can easily calculate the power required for this process. So that is nothing but your total drawing load into the velocity of drawing. So that is again a simple physics. We all know that force into velocity is power, so this v is like velocity of wire, okay, with which we are drawing this this tube. Okay, so as we have seen, like this sigma 2 should be lesser than sigma y, and in maximum case that sigma 2 can be equal to sigma y, and at that moment we will get the maximum reduction in the rod, because if say how much maximum reduction we can get from this process, that is the aim. So for that purpose we have to consider a condition where sigma 2 will become equal to sigma y. So this is the condition for maximum reduction, maximum possible reduction in this process. Okay, maximum possible reduction, and by applying this condition, finally we get the maximum the reduction, maximum possible reduction, and the maximum possible draft. We have seen the two terminologies as draft and reduction. So the maximum possible draft is say 2.72, and the maximum percentage reduction we get is 63%. So this is again an important thing that is related to wire drawing, how much maximum draft you can get and how much maximum reduction in area we can get from this process. So this is just basic terminologies and how we can correlate the different terms involved in this drawing, how we can find out the drawing load, then power, how the maximum reduction in wire area is possible, by which condition. So this is the basic. Then again one thing is there is like tube drawing. As we seen, we were drawing a solid wire. Now if we want to reduce the thickness of a existing tube, then the process is like wire drawing. So in this process we use a mandrel, and with this mandrel, this say this is our original thickness and this is our final thickness. So the thickness of say the thickness is reduced with this, and with the help of mandrel here. So we are putting a mandrel inside this tube, and we are getting the required wall thickness of the tube. So again here we are applying the stress, the force because of which the stress is getting induced. Now here we are keeping this die as a stationary, and with the type of mandrel we can either have a uniform bore size, or we can vary the cross section. Say if we want to vary the ID, then we can use a conical mandrel. So if the mandrel is like, when I say a rectangular mandrel, it is like this. So this is rectangular mandrel, so it will not be having any angle. So but when I want say variation in the ID of the tube, I have to go for a conical mandrel. So again it will have a angle that will be cone angle. So let's say this 2 gamma is our cone angle of our conical mandrel, right? So this is the condition, like if you want uniform cross section, go for rectangular mandrel, and if you want the variable ID, we have to go for the conical mandrel. Now here, as in the wire drawing, we have seen that there was only one coefficient of friction, like here, but again here we are using a mandrel, so there will be friction between the mandrel and the ID of the tube. So we have like mu1, that is the coefficient of friction between the say OD and the wall of die, right? This is the wall of die and this is the OD of tube, and I have mu2 as coefficient of friction, say between the ID of the tube and say OD of mandrel, right? Because it is at this portion, so it is like ID of the tube and the OD of the mandrel, and here it's like OD of the tube and the wall of the this die. So this is our die, right? Which is stationary, and we are moving this this total mandrel and tube against the die. So die is stationary. So this is like the coefficient of frictions. Now depending on the type of mandrel, this mandrel can be a stationary mandrel, or it can be a moving mandrel, or it can be a floating mandrel. So depending on that, we have seen we have a constant value of we have a value of p which can be calculated here like mu1 plus mu2 divided by, we have tan alpha minus here we have tan gamma. Now in the previous case we have seen that this b was mu1 by tan alpha only, so that is nothing but mu1 into cot alpha. We have seen that. Now here, as this mu2 value is getting incorporated, we have a value of b as mu1 plus minus mu2. Now why this plus minus we will see, because this mu2 value depends upon whether this mandrel is stationary, moving or floating. So that's why I have written here like plus and minus. And then we have alpha as our cone angle, which we have seen, and that will be half cone angle because 2 alpha is the cone angle. And then gamma, here we have seen the 2 gamma is our cone angle of the mandrel. So that is important. This is cone angle of say here we have mandrel, like, okay, so that is important. So we have mandrel here, and that is of mandrel only. So gamma is for mandrel and alpha is our cone angle. See, we should write here and that will be more clear. This is our 2 alpha we have seen, right? So this is our B value. Now let's go into some details, like we have 3 types of mandrel. First one is stationary mandrel. Okay, so in this case mandrel is stationary, so we can use both the conical or rectangular mandrel, and we have a value of B as mu1 plus mu2 divided by tan alpha minus tan gamma, right? Here we can use both straight or conical mandrel. If we go for a cylindrical mandrel, we will not have any gamma value, and if we go for a conical mandrel, then we will have this gamma value. And again we can calculate the forces similar as that of the previous cases. Now here we have seen like mu1 plus mu2 because both coefficient of frictions are acting in the same direction, or rather we can say that the friction in both these cases is acting in the same direction, and that's why we are adding them. Okay, now the second case is like moving mandrel. So the second case is like moving mandrel. Now when I say moving mandrel, the mandrel is moving relative to the tube, because I am drawing the tube and there is a mandrel inside the tube. So there are cases like mandrel is moving with the same velocity of tube, or the mandrel is leading the tube, and that means it has a higher velocity than the tube, or the third case is the mandrel is having the lesser velocity than the tube. So if we consider like mandrel is moving along the tube with the same velocity. So if we consider like velocity of mandrel say is equal to velocity of tube. Okay, now this is the case. So what will happen is as we have seen the mu2, now in this case the mu2 will become 0 because there is no relative motion, because both are moving together having the same velocity. That's why this coefficient of friction, that means the mu2 will be 0, and gamma is also 0. We can't use conical mandrel here, so conical mandrel cannot be used here, right? In this case, so with this we can write the value of B is like we have seen that mu2 is 0 and gamma is 0, so we just have mu1 by tan alpha, and that is nothing but mu1 cot alpha, right? So we have seen this case in the tube drawing. So it is like the case of tube drawing only, because the mandrel is moving with the same velocity, and that's why we have this case. Now say if the mandrel velocity is different, so if we have like mandrel velocity say mandrel velocity is lesser than the velocity of tube, right? So now what will happen in this case? The mandrel is moving in like backward direction, because now let's focus again on say this diagram. Okay, now we have a mandrel here, right, in this section. Now the velocity of mandrel is less than the velocity of tube, right? The velocity of tube is greater, so this mandrel, let's say m, its motion will be in opposite direction. The mandrel will move in the backward direction, so because of that the tube is moving in this forward direction, like, and the mandrel is moving in backward direction, right? As their direction of motion is different, the coefficient of friction will be in opposite direction. Because the tube is moving in forward direction, its friction will be acting in the opposite direction, and the mandrel is moving in backward direction, so the friction force will be acting in this direction. So both these values are like opposite. So in this case, again the conical mandrel cannot be used, and we can have a value like mu1 minus mu2 divided by tan alpha. So now we can know that why this is minus, as initially I have written here like plus and minus. So in first case, in the first case, the stationary mandrel, we have seen that was the plus one, and like in this case it is like mu1 minus mu2, because the mandrel is moving in the backward direction, that is opposite direction of the tube. So that's why we can write it as mu1 minus mu2. So if the mandrel velocity can be greater than the tube velocity, and in that case the mandrel will be moving in the forward direction only, and in that case the mu2 value will be positive, and we can have mu1 plus mu2 divided by tan alpha. So that will be the case. So these are some of the basic things, and that are generally not considered or not taught in our curriculum, but this is like we can say the engineering or the physics or the different subjects that are involved in this production technology. So I hope you understood this drawing process, and if you have any doubts, please do write into the comment section, and we can discuss over there. Until then, stay happy and stay home. Thank you.